So good morning friends. I'm going to explain in this particular video I'm going to explain the boundary layer theory, basics of boundary layer theory. I'm Sushan Lal Babu, Assistant Professor Aerospace Division, Karunya Institute of Technology and Science, Coimbatore. So just an introduction. What is a viscous flow? That is a major part of this boundary layer formation. So you can see here a flat plate of so here this is a you can see this flat plate here, and it is having formation of boundary layer over the flat plate. So free stream velocity will be approaching. So here in this direction the free stream velocity will be approaching. That free stream, why it is called free stream, means see, layer by layer formation, all these layers are having same velocity. Okay, and once it reaches this leading edge of this particular plate, then it will start forming the boundary layer. Why? Because the first layer which is approaching will take the velocity of first layer, means what, that fluid. Okay, first layer of fluid will take the velocity of same as that the surface velocity will be same as that of the surface. That is, velocity will become zero, and the layer, the top, the next layer which is about to flow over that particular surface will, with that, this first layer will drag the layer above it. It will hold it back. Don't go, I am still here, so you also have to be with me. So it will hold it back, but anyway, because of the flexibility, it will move. That particle will reduce. If speed will reduce, no, it won't become stationary as the first layer, but the speed it will be reduced. So since the second layer speed reduce, again it will drag the another just above layer. Okay, like that it will continue. And these things, because of why this layer by layer drag or something happening. Drag is nothing but because of what? Friction. Okay, friction, or we can see that in the case of fluid it is nothing but viscosity. Okay, so viscosity is nothing but the, we can explain it as the intermolecular force of attraction. So the fluid attraction, it is the viscosity, and because of that attraction this drag phenomena is happening and velocity will be reduced. Okay, so within the boundary layer, so here, but these fluid layers are moving with here. Okay, same speed. Only these three becomes so yeah, just have to extend it here, because uh, yes, so here it's reached this velocity. That's why here it reaches. So this, you can see this formation, see, and here it will be straight, same. And here if you say, if you take a line here, then it will like this, it will increase like this. So here everywhere you will can see u infinity, but here it is less than u infinity. See, it is reducing and becoming zero. So how we can define the range of this boundary layer formation? So wherever the velocity becomes approximately equal to 99% of u infinity, till then the boundary layer formation exists. So that is what explained here. The outside boundary of a boundary layer is usually chosen as the point where the velocity of the flow is 99% of the free stream value. Okay, next is same explanation. So here little more clarity is there. So u zero means u infinity only. This is, so this means u infinity. So everywhere you can see same velocity, but in, say, when once it reach in above the surface of this flat plate, then you can see this here is u0, here outside layer u0 only, but here it is less than u infinity. This much, this is less than u infinity, this is less than u infinity. Okay, so here when we reach, after some time it will become transition, and after that it will become turbulent. Okay, so if you consider the turbulent boundary layer region, there exists a viscous sublayer very close to the surface, and then a buffer layer, then overlap layer, and then turbulent layer. So inside the viscous sublayer the flow will be, so the profile will be almost linear. See, you can see that approximately linear, you can say that it is linear. And this turbulent, this is almost flat also. Okay, so it's not quadratic, but you can say, for more precisely, you can say it's logarithmic in nature. So that is a explanation given in this particular picture. Then this one what general example. So some toothpaste if you are taking, and we are squeezing this toothpaste, you are squeezing it in this direction. Okay, it will come out. So it will come out if the no slip condition exists, means it will be parabolic. Okay, no slip means here the layer will not move. Okay, but there is no slip means it will be like this. No slip is not existing means because it will be very smooth, there is no friction between the tube wall and the fluid layer, then it will come out like this. But if no slip condition exists means it will be parabolic. This is the profile we explained, this parabolic profile we are getting in the laminar flow. Hmm? Another thing. Okay, so another example. So this is the example where one truck with marble slabs. So this one layer for first layer, 1 2 3 4, like that. So different layers are there of solid layers. Okay, solid layers we are discussing in fluid, but an example with solid we are trying to explain. Okay, so this is those it start moving, it start rotating and it start moving. Okay, moving in this direction, it arrow is shown and suddenly it stops. Suddenly stops means what? One by one. So what happened to this layer? Its velocity will be 0, same as that of the surface, because this is a solid surface with 0 velocity. So first layer will take the velocity of that surface, the next one will drag, next one the dragging phenomenon will happen. This same way the fluid also will experience the same drag. So many layers. So these are the layers. Okay, you can see the yellow see layer by layer formation. With the same velocity it is approaching that slab. Okay, so once it get into the slab, what will happen? It will see, it will start so first layer will drag the just above layer, and that layer will drag the another just above the layer. So like that the boundary layer formation will happen, and this thickness is explained here. So thickness is delta is increasing with x. With the increase in the x, the delta is increasing. That is what they are mentioning here, and this is the limit where u becomes approximately equal to 0.99 u infinity. Okay, so within the boundary layer, see this is will be less than okay, or equal to 0.99 u infinity. And this is same picture explanation, same explanations, and some other parameters are there, that is called Reynolds number. Okay, Reynolds number. So Reynolds number means Reynolds number is nothing but the ratio of what inertial Re is nothing but inertial force by viscous force. So inertial force dominating means very too turbulent it will become, and viscous force dominating means layer by layer formation we can see. So viscous force dominating means layer by layer, laminar, layer by layer formation we can see. Okay, but viscous force is reducing, that implies inertial force is too high, implies what? Very mixing. See, layer will recirculate, otherwise it will form like one over the other, one over the other. This is called laminar, but this is called turbulent. Okay, so and this laminar and turbulent transition will happen at what Reynolds number the transition will happen. So laminar means over the flat plate, if Re is less than 3 into less than or equal to 3 into 10 power 5, then laminar. If it is between 10 power 5, 3 into 10 power 5 and 5 into 10 power 5, it is transition. And if it is greater than 5 into 10 power 5 means turbulent. Okay, so that is the explanation for, and Re is a non-dimensionalized number, and the for Re expression is like this. Okay, fine. Thank you.